Welcome, ladies and gentlemen. In this two-part session, we'll cover IoT on-premise as well as machine learning in ArcGIS. So without further ado, let's take a look at what we'll be covering in this two-part session. We will first take a look at a brief introduction of IoT, or Internet of Things as it's called. Then we'll try to gain a better understanding of a typical IoT solution by taking a look at a generic IoT solution blueprint. Next, we will see how ArcGIS as an IoT platform enables geospatial insights with your IoT solution. This will conclude the first half of the session about IoT on-premise. Next, we'll move on to discuss what machine learning is in ArcGIS and AI context. Then we'll be followed by the categories of tools in ArcGIS Pro that aid this process. Finally, we'll explore the machine learning workflow with a brief case study to illustrate the processes better, with an example to round up our discussion on machine learning. Now, the term IoT was first coined by Kevin Ashton in 1999. In layman terms, the Internet of Things is basically devices that allow exchange of information between human beings and devices that add value to our lives. According to The Economist, the use of IoT devices is expected to be deep and wide, as illustrated by the diverse applications they may have in relation to humans, and fast-changing as depicted by the chips in the picture on the left. According to these stats from Newsweek, the number of IoT devices being used has significantly increased since 2009. The use in Asia Pacific alone is expected to increase fivefold by 2021. Another chart shows an expected increase in specifically cellular and non-cellular IoT devices by 2021. Now let's take a look at a general blueprint for IoT solution and how ArcGIS products facilitate their capabilities on-premise in the next slide. So first up, we have ingestion, which is the input from sensors. Then we have streaming analytics and policies, which consist of the rules for consumption of the sensor data. Then we have actions, which will be the outputs by the actuators. Then we have data store for storing the data. We have device management, which if needed can be incorporated into the ArcGIS platform. Then we have batch analytics, which is basically for big data analytics. We then have the management console, which is for admin supervision of the process. Now, finally, we can do a visualization for visualizing the analytics in an aesthetically pleasing interface. Now, ArcGIS manages to enable geospatial insights with your IoT solution as an IoT platform. For ingestion, we have the GeoEvent server input connectors. For streaming analytics and policies, we have the GeoEvent services. For actions, we have the GeoEvent output connectors. And then for data store, we have the spatial-temporal big data store. For device management, for those requiring this functionality, another IoT platform can be complemented with the ArcGIS platform. For batch analytics, we have the GeoAnalytics server. For management console, we have the portal as well as the GeoEvent server. And finally, for visualization, we have map, feature services, operation dashboards, insights, and story maps, to name a few. So this concludes our discussion about IoT on-premise. Now let's move on to the second part of the session, which is about machine learning. The field of artificial intelligence has progressed rapidly in the recent years, matching or in some cases even surpassing human accuracy at tasks such as image recognition, reading comprehension, and translating text. The intersection of GIS and AI is creating massive opportunities that weren't possible before. AI, broadly speaking, is the ability of computers to perform a task that typically requires some level of human intelligence. Machine learning is one type of engine that makes this possible by using data-driven algorithms to learn from data. Deep learning uses computer-generated neural networks, which are inspired by and loosely resemble the human brain, to solve problems and make predictions. A graphic in the next slide will demonstrate how a neural network creates a model. So the orange phase shows the network attempting to classify the object. The green phase represents the network testing the result. And the blue phase depicts the network adjusting the parameters through backpropagation. Now do note that this graphic is an oversimplification of the neural network learning process. There are only a few activations shown in this graphic, whereas in reality, there will be hundreds of these activations. Now, machine learning has been a core component of spatial analysis in GIS. These tools and algorithms have been applied to geoprocessing tools to solve problems in four broad categories. With classification, we can use vector machine algorithms to create land cover classification layers. Another example is clustering, which lets you process large quantities of input point data, identify the meaningful clusters within them, and separate them from the sparse noise. We also have prediction algorithms such as geographically weighted regression that gives you the ability to model spatially varying relationships. Now, these methods work well in several areas, but they need experts to identify or feed in those factors or features that affect the outcome. So this is where the deep learning comes into play. We will explore these categories in greater detail in the next few slides. So first up, we have prediction, which is about using the known to estimate the unknown. Now, prediction works in three basic principles: using known parameters to predict those that are not known, using them to establish a pattern. The pattern can then be used to predict values in varying space and time. Now, in the second category, clustering is the grouping of observations based on similarities of values or locations. In ArcGIS itself, we have spatially constrained multivariate clustering, which finds spatially contiguous clusters of features. We also have the multivariate clustering, which finds natural clusters of features based on attribute values. We then have the density-based clustering, which finds clusters of point features based on their spatial distribution. We also have the hotspot analysis, which identifies statistically significant hotspots and cold spots. We also have the cluster and outlier analysis, which is similar to the hotspot analysis, but it also allows you to identify outliers. We then have the space and time pattern mining toolbox, which contains tools for analyzing data distributions and patterns in the context of both space and time. Now, in summary, clustering tool methods can be used to do analysis, such as segment school district based on socioeconomic and demographic characteristics to find areas with dense social media activity that happen after a natural disaster. Now, in the third category, which is classification, it is the process of deciding to which category an object should be aligned based on a training data set. Now, ArcGIS includes many classification methods focused on remotely sensed data. These tools analyze pixel values and configurations to characterize pixels. Some examples include delineating land use types or identifying areas of forest loss. So we can do things like detecting and categorizing objects. We can use the imagery and other remotely sensed data. We can also analyze pixel values and classify them into groups. Now, some classification tools include maximum likelihood classification, which, as the name suggests, performs a maximum likelihood classification on a set of raster bands and creates a classified raster as an output. We also have classification tools like random trees as well as support vector machine. Now, classification tools overall help to identify types of images from inputs in order to smoothen the analysis process. Now that we've seen the three categories of tools available within ArcGIS Pro to aid in machine learning, let's dive into the machine learning workflow and follow this up with a case study. Now, machine learning is incorporated into the ArcGIS environment in a three-part process. In the first part, a GIS professional uses ArcGIS Pro to generate training samples to export the data. In part 2, which is mainly done outside of ArcGIS in a Python environment, where data scientists will incorporate the training samples created earlier into a learning framework like TensorFlow in conjunction with a machine learning algorithm or technique to generate model definitions. This is probably the most intensive part of this entire workflow. Now, in the final part, which is done back in the Pro environment, a new set of data and the model created in the second step is used to output the predicted results. For this case study, we are interested in finding all the buildings within a study area to create a building inventory. Now, we have raster data from SciSat sensor to use for this inventory. The desired study area covers a large region, and we are interested in detecting a specific object, buildings in this case. And we want to do this in a systematic manner. To aid in the image classification, a data scientist has been added to the team to use a neural network to develop training data. In order to create a model, the data scientist needs the training data as well as the image chips. Now, our job would be to create the training data for the data scientist and then use the model that he generates back in the environment to predict the objects. And now let's have a look at the case study. Now we're in the ArcGIS Pro environment. I'll go to project in Python to make sure that we have the correct packages for this workflow. So in this, I'm using TensorFlow. So I have to make sure the TensorFlow package is included inside the environment. As you can see, I've already added it in. Now moving back. So this is the raster data we'll be using to create the training samples. So let me just click on the training sample that I have pre-created. So these are polygons that I have created to identify buildings within this raster data. So when I bring up this attribute table, you can see that I have already classified this class name as well as class value. So the class name is houses and the class value here is 2. Now what we're going to do is use this tool called export training data for deep learning. And we're going to input all the relevant inputs in order to generate the model, the training sample, sorry. So let's input all the feature classes. So the training sample is basically the red color polygon that I'm using in this picture right now. So now I've already pre-run this tool, so my output is already present. I'm going to navigate to the location of this training sample. So under data, training data, I have this Esri model definition.emd. So this is basically what the output is going to look like. Let's click on it. So you can see the framework, model configuration, model type, etc. all need to be named by the data scientist itself. Right now it just contains example, but it needs to be identified. Now coming back to our ArcGIS Pro environment. Wait, let me look at where the data is stored. Okay, so we have this model that was passed to us by a data scientist. So it contains the framework. In this case, we're using TensorFlow. So it has already been predefined. So imagine I did that training sample data creation a few times, and then I passed that data to a data scientist. So he will use that data to churn out this model along with the PB file. And then this will be used in order for us to predict building locations in another raster file. So let's have a look at the one we want to predict the images in. So let's go to the new data, which is Egypt sample.tif. So inside here, we're going to predict where the buildings are located based on our model that was generated by the data scientist. So in this case, we are going to use this tool called detect objects using deep learning. So here we have to input the raster data, which in this case will be the new set, which is Egypt sample.tif. And then we have to locate the output or detected objects folder. So I'm just going to call this detected buildings in this case. And as for the model definition, we're going to use that model that was passed by the data scientist. Okay, it takes a bit of time to populate the arguments. Okay, there we have it. And then we are going to run the tool. So since I've already pre-run the tool, I already have the output inside geodatabase. So let's move on to that location. So I have it in DL_data. All you have to do is refresh it if it doesn't show up here, and then you can drag it into the map. And then inside your detected buildings, it will show you all the images that have been classified using the model that was passed by the data scientist. So here you can see that we have a few buildings that are located by these blue polygons. And you can see the class is exactly the same as what we identified in our training samples earlier. However, if I zoom into some locations, you'll see that there's some redundant sets of data. Within a big identifier of a building, there's another small polygon that identifies that same building. So you will have these shortfalls in your model as well. But in order to overcome all these challenges, what we can do is to basically have different orientations of the object in our training samples, as well as have objects of different clarity. So for this case study, the resources that I used was ArcGIS Pro 2.5, the advanced version. We also have the image analyst as well as the spatial analyst. And then I also use the SciSat sensor data. That brings to the end of my presentation. Thank you.